Hello, everyone, and welcome to today's Explainer. I am absolutely thrilled to have you here. If you're joining us for the first time, welcome to our software engineering lecture series. Grab a seat, get your notebooks ready, and let's dive right in. Today, we're opening up Chapter 24 of our textbook, which offers a truly fascinating look at quality management and software quality. Now, whether you're aiming to be a lead developer, a system architect, or a project manager, the concepts we're going to cover today are completely fundamental to building systems that actually survive out there in the real world. So let's get started.
Here is our roadmap for today's session. First, we'll cover an intro to quality management, then assurance, control, and independence. From there, we'll talk about defining the quality plan, before shifting gears to software versus manufacturing quality. Then, we'll explore attributes and quality culture, and finally, wrap things up with an exam summary and next steps.
All right, Part 1, Intro to Quality Management. What exactly is quality? Before we can dive into any specific technical metrics or testing frameworks, we really need to understand the overarching goal of quality management. To figure that out, let's look at the formal definition. Quality management, or QM, is the set of processes ensuring a developed software system is fit for purpose, meets user needs, performs efficiently, and is delivered on time and budget. Now, that phrase right there, fit for purpose, is incredibly important. I highly recommend highlighting that in your notes. Fit for purpose is literally the bedrock of everything we're going to discuss today. It means the software does exactly what the client actually needs it to do, it does it reliably, and it does it within the constraints they gave us. Because, let's be honest, a beautiful, perfectly coded program is completely useless if it doesn't solve the user's actual problem, right?
Now, quality management doesn't just happen by magic. It operates on two very distinct levels. On one side, we have the organizational level. This is where company-wide frameworks and standards are set. Think of this as the master rulebook for the entire software firm, establishing how every team should generally operate. On the other side, we have the project level. This is where you're taking those overarching standards and applying them to a specific team building a specific product and checking their actual outputs. You really need both. Without organizational standards, every project is just chaotic. But without project-level checking, your organizational standards are just empty words on a page. Section 2. Assurance, control, and independence. Quality management is actually an umbrella term that breaks down into two highly specific concepts, and they both have strong roots in traditional manufacturing history. Let's define them.
First up is quality assurance, or QA. The definition here is key. QA is the definition of processes and standards designed to lead to high-quality products and prevent bugs. The absolute most crucial point here is that QA is about prevention. There is a very common misconception out there, even among working professionals, that QA just means testing the software. That is incorrect. Quality assurance happens before and during development. It's about setting up the right coding standards, the right review processes, and the right methodologies so that bugs are never written in the first place. And that brings us to quality control, or QC. QC is the application of defined quality processes to weed out products that are not of the required level of quality. If QA is all about preventing bugs, QC is the actual checking and testing of the product to catch the bugs that inevitably slipped through. It's the filter at the very end of the line. So a great way to remember this for your exams, QA defines the process, QC tests the product. This distinction brilliantly illustrates a major real-world problem, the tempted manager. Why must the quality management team remain entirely independent from the development team? Well, imagine a project manager who has a strict deadline and a rapidly shrinking budget. It's Friday, the software is due to the client on Monday, and the code is just full of errors. That project manager is naturally going to be tempted to ship bad code just to hit the deadline. If the QM team reports directly to that manager, they're going to be silenced. That is exactly why an independent QM team is absolutely crucial. They protect the quality of the software because they don't answer to the project manager, they answer to higher management. They can remain impartial. Okay, let's do a quick mini recap before we move forward. Ensure you really recognize these distinctions. Quality management is the overarching goal of making software fit for purpose. Underneath that umbrella, QA prevents bugs by defining processes, and QC catches bugs by testing the product. And finally, independent QM teams enforce these standards impartially, completely safe from the intense pressure of tight budgets and schedules.
Section 3. Defining the quality plan. So, how is project-level quality actually formalized? How does a whole team agree on what good looks like? Through one specific document. This is the quality plan. By definition, it's a concise document setting out the desired software qualities, goals, and how they will be assessed for a specific project. I want to strongly emphasize the word concise here. The textbook makes it very, very clear. If you write a massive 100-page quality plan, literally no one on the engineering team will read it, and it becomes completely useless. It has to be short, punchy, and incredibly direct.
To keep things concise, we generally use Humphrey's classic 5-point outline structure for a quality plan. Let's rapidly break these down. 1. Product introduction. Simply, what are we building and who is it for? 2. Product plans. What are our most critical release dates? 3. Process descriptions. What coding standards and processes are we actually committing to using? 4. Quality goals. What specific attributes are most critical for this particular system? And finally, 5. Risks and risk management. What could severely impact our quality, and how do we plan to mitigate it? It's simple, structured, and super easy for any developer to digest.
Let's pause for another quick recap. The quality plan is essentially your project's compass. It acts as the shared understanding of quality for the entire engineering team. And just remember, it absolutely must be concise, ideally following Humphrey's straightforward 5-point structure so that people actually use it day to day. Section 4. Software versus manufacturing quality. We're now shifting our focus slightly to section 24.1 from the textbook, moving away from the management processes and looking at the very nature of software itself.
What's really fascinating here is the analogy of the bolt versus the bug. You see, in traditional manufacturing, quality is highly objective. If a factory is making a 10mm bolt, we have objective tolerances. If it measures 10.1 millimeters, it passes. If it measures 12 millimeters, it immediately fails. You can hold it, measure it, and prove it. Software just isn't like that. Software quality is highly subjective and intangible. You can't take a physical ruler and measure a piece of code to definitively see if it's good.
The textbook gives us 3 specific reasons why software quality is so incredibly subjective. First, ambiguous requirements. Clients rarely know exactly what they want in technical terms, so developers have to interpret things. Second, stakeholder compromise. The marketing team might want a super flashy interface, while the security team wants a completely locked down system. Whatever you end up building is a compromise, meaning someone, somewhere, will always think the quality is lacking. And third, unmeasurable attributes. You simply cannot easily measure something like maintainability directly. How do you assign a definitive mathematical score to how easy a program will be to update 5 years from now? You just can't.
So, recapping section 24.1's core argument, software quality fundamentally requires human judgment because it completely lacks the objective, physical tolerances of traditional manufacturing. Deciding if software is truly fit for purpose is ultimately a highly subjective decision made by the quality management team.
Section 5. Attributes and quality culture. This raises a big question. If software quality is so subjective, how on earth do we actually judge it? Well, we have to look at specific attributes. We judge subjective quality by evaluating non-functional attributes. These are the characteristics of the system as a whole. Things like its overall behavior, its response time, its security, and its reliability. Notice that this is not about specific features or buttons. Users might be slightly annoyed if a specific feature is missing, and they might even find a workaround. But they absolutely cannot work around a system that crashes constantly, or one that takes 10 minutes to load a single page. The non-functional attributes define the true underlying behavior of the system. According to the textbook, these attributes are the true measures of subjective software quality. We're talking about attributes like security, which is how well the system protects user data, and efficiency, which dictates speed and resource use. But we also have things like reliability, how often it fails, and resilience, how well it bounces back when it does fail. There's also robustness, which is how it handles unexpected or just plain bad inputs, and maintainability, how easily the codebase can be updated in the future. When the QM team is trying to decide if the software is actually fit for purpose, these are the exact attributes they are carefully assessing. Okay, please put a massive star next to this in your notes, because this is an absolutely crucial exam concept: trade-offs in non-functional attributes. You cannot optimize for everything. It's literally impossible. For example, if you want to maximize security, you often have to add layers of encryption and multiple authentication checks. But what happens then? You severely minimize the system's efficiency and speed. It becomes sluggish. The quality plan exists specifically to dictate which attributes win these trade-offs. You have to prioritize based on what the client actually needs most.
To wrap up our conceptual material today, I really want to leave you with this idea. Standardizing processes, defining QA and QC, writing a concise quality plan, all of this is vital. But it isn't enough on its own. True quality management requires a culture where engineers take pride in their craft. The ultimate goal of a QM manager isn't just to write rules, it's to foster a quality culture where developers genuinely care about the behavior of their code, even when no one is checking up on them.
Section 6, Exam Summary and Next Steps. All right, let's transition into our comprehensive review. Get your pens ready. This is where we lock in the absolute key concepts you need to take away from this lecture.
So to summarize the most critical definitions from today, quality management is making sure software is fit for purpose. Quality assurance prevents bugs. Quality control catches bugs. The quality plan is your concise, shared understanding of project goals. And non-functional attributes, like reliability and efficiency, are how we judge the highly subjective nature of software. Please do not forget the exam focus on trade-offs. You cannot optimize everything, you must prioritize. In our next session, we're going to move on to Section 24.2, where we'll discuss software standards. But until then, I want to leave you with a provocative question to ponder. If software quality is ultimately subjective, and you completely lack the objective measurements of a factory manufacturer, how will you personally define fit for purpose in your very next program? Think about that for a bit. Thank you so much for learning with me today, and I will see you in the next explainer.